The science of predicting an asteroid impact. You've no doubt seen headlines like, "Astronomers say space rock may hit Earth in the not-too-distant future." We usually see such warnings about one or two objects every year. The latest iteration concerns asteroid 2024 YR4, which may be up to 100 meters wide, and as of now has a greater than 2% chance of striking our planet in 2032. How can scientists predict these potential impacts? The answer lies in centuries-old principles discovered by German astronomer Johannes Kepler in the 17th century. Kepler's orbital laws help astronomers predict the paths of asteroids using modern telescopes, digital cameras, and powerful computers. Every night, telescopic observatories scan the skies for moving objects against the static stars. Once identified, astronomers apply Kepler's equations to map these asteroids' orbits. These orbits come in elliptical, parabolic, or hyperbolic shapes. Elliptical orbits, like those of most asteroids, mean these objects are bound to the Sun unless acted upon by external forces. Predicting the future position of an asteroid requires accurate observations taken over time. Miscalculations, even minor ones, can lead to significantly different predictions. To achieve accurate predictions, astronomers rely heavily on repeated observations from multiple observatories worldwide. By tracking the asteroid's position relative to known stars, scientists can refine their calculations and reduce uncertainties. These observations are recorded and analyzed using sophisticated software that models the object's trajectory over time. Additionally, gravitational interactions with other celestial bodies, such as planets or even large asteroids, can alter the path of these objects. This phenomenon, known as gravitational perturbation, requires ongoing monitoring to adjust predictions accordingly. For instance, Jupiter's immense gravitational field significantly influences the trajectories of many near-Earth objects. Another critical factor is the Yarkovsky effect, a small force exerted on an asteroid due to the way it absorbs sunlight and re-emits heat. This subtle force can cause gradual changes in the asteroid's orbit over decades. Scientists simulate these effects to project possible future positions more accurately. Asteroid detection efforts have become more advanced with the introduction of wide-field survey telescopes. These instruments capture vast areas of the night sky in a single image, making it easier to identify new objects and track known ones. The Pan-STARRS project in Hawaii and the Catalina Sky Survey in Arizona are two prominent examples of such initiatives. Public awareness and international cooperation have also increased. Organizations like NASA's Planetary Defense Coordination Office work alongside international space agencies to share data and collaborate on potential mitigation strategies. Understanding asteroid behavior requires both historical context and cutting-edge technology. While the risk of a catastrophic impact remains low, continued research and vigilance are essential to safeguard our planet. An asteroid named 99,942 Apophis was discovered in 2004. Early calculations indicated a 2.7% chance it might hit Earth in 2029. Scientists initially believed it would miss us, but later recalculations showed how close it would come. Just 30,000 kilometers away, closer than many satellites. This proximity makes Apophis one of the most closely monitored asteroids in the world. The discovery of its potential trajectory sparked intense research efforts, with astronomers working tirelessly to improve calculations and reduce uncertainties. Tracking its motion required observations from multiple observatories across the globe, each contributing critical data to refine the asteroid's orbital parameters. The concerns surrounding Apophis highlighted the challenges inherent in asteroid prediction. Small variations in measurements can significantly affect long-term predictions. For example, changes in the asteroid's surface composition due to solar heating or interactions with other celestial bodies could alter its orbit slightly. These minor shifts, although seemingly inconsequential, might lead to drastically different predictions when extrapolated over several years. Understanding Apophis's trajectory involved simulating countless potential orbital paths using advanced computer models. Scientists ran these simulations to predict how gravitational interactions with Earth, the Moon, and other objects might influence its future path. These simulations revealed that Apophis would make an exceptionally close pass in 2029, providing a unique opportunity to study a near-Earth object up close. Despite the initial concerns, subsequent calculations showed that Apophis would miss Earth in 2029. However, this event serves as a stark reminder of the importance of continued monitoring. If calculations had remained imprecise, the consequences could have been severe. The asteroid's size and velocity would result in an impact with catastrophic consequences if it were on a collision course. The hypothetical scenario of Apophis hitting Earth prompts consideration of the potential impact effects. The energy released upon impact would depend on its size, speed, and impact location. With a diameter of 340 meters, Apophis could cause regional devastation if it struck a populated area. Even an oceanic impact could generate tsunamis capable of affecting coastal communities across continents. To better understand the mechanics of such an impact, scientists have studied past asteroid events. The Tunguska event of 1908, which flattened thousands of square kilometers of Siberian forest, serves as a cautionary tale. Researchers analyze these historical occurrences to model potential outcomes more accurately and improve predictive techniques. The asteroid's potential interaction with Earth's gravity during its close approach in 2029 could alter its trajectory for subsequent passes. This phenomenon, known as a gravitational keyhole, occurs when an asteroid passes through a region of space that positions it for a future collision. Monitoring Apophis's path during its 2029 approach will provide invaluable data for refining predictive models and understanding gravitational interactions. Furthermore, scientists must account for the Yarkovsky effect, where thermal radiation from the asteroid's surface can induce slight orbital changes over time. Apophis, like many asteroids, rotates as it orbits the Sun, causing asymmetrical heat distribution that influences its path subtly but significantly. Public interest in Apophis has spurred increased funding and research into planetary defense initiatives. The development of advanced tracking systems, such as NASA's Near-Earth Object Observations (NEOO) program, aims to enhance detection capabilities and mitigate potential threats. International collaboration is essential, as the implications of an asteroid impact transcend national borders. Apophis is not the first asteroid to cause global concern. Historical records reveal numerous instances of asteroid encounters, some with devastating outcomes. The Chicxulub impact, for instance, occurred 66 million years ago and led to the extinction of approximately 75% of Earth's species, including the dinosaurs. The crater it left behind, spanning over 180 kilometers, serves as a stark reminder of the destructive potential of these celestial objects. The 2013 Chelyabinsk meteor event further underscores the unpredictability of these cosmic intruders. The explosion occurred over the Russian city of Chelyabinsk with the force of 500 kilotons of TNT, injuring over 1,500 people and causing extensive damage to buildings. Unlike Apophis, the Chelyabinsk meteor was relatively small, measuring only 20 meters across, yet its impact was significant. Understanding these past events allows scientists to better anticipate and prepare for potential future impacts. Advanced computer simulations help recreate historical asteroid trajectories, providing insights into the factors influencing their paths and the subsequent effects of their collisions. The psychological impact of asteroid threats. Beyond the physical and environmental risks, the mere possibility of an asteroid impact can cause widespread public anxiety. Media coverage of close approaches, such as Apophis's predicted pass in 2029, often sensationalizes the potential threat, leading to misinformation and panic. Educational campaigns play a crucial role in mitigating these fears by providing accurate science-based information about asteroid detection and planetary defense. Psychologists have studied the phenomenon of impact anxiety, noting that uncertainty about cosmic threats can contribute to heightened societal stress. Public discussions, open forums with scientists, and interactive educational programs in schools can help foster a more informed and resilient public response. Technological innovations in monitoring Apophis. Technological advancements have significantly improved our ability to monitor Apophis and other near-Earth objects, NEOs. Radar imaging, for example, allows scientists to capture high-resolution images of asteroids, revealing surface features and rotational dynamics. NASA's Goldstone solar system, radar, and the Arecibo Observatory have both contributed valuable data about Apophis's physical characteristics. In addition to ground-based observations, space missions like the OSIRIS-REx mission to asteroid Bennu provide direct, in-situ measurements of asteroid composition and behavior. These missions inform broader planetary defense strategies by offering empirical data on asteroid structure and potential response to deflection techniques. The role of international collaboration. The threat posed by Apophis and similar asteroids transcends national borders, necessitating global cooperation. The International Asteroid Warning Network, IAWN, and the Space Mission Planning Advisory Group, ADS-SMP-AG, serve as key platforms for coordinating international efforts. These organizations facilitate the sharing of observational data, research findings, and best practices for impact mitigation. Countries around the world contribute to these efforts through telescope installations, research initiatives, and policy development. For instance, ESA's Fly-Eye telescope in Italy is designed to automatically scan the sky for NEOs, complementing NASA's efforts in planetary defense. As Apophis's 2029 flyby approaches, scientists remain vigilant. The data collected during this close encounter will refine our understanding of asteroid dynamics and improve predictive models for future objects. Long-term monitoring of Apophis's orbit will continue, particularly as its next significant close approach in 2068 presents another opportunity for observation. Ultimately, the case of Apophis illustrates the complexities and challenges of asteroid prediction. Continuous monitoring, advanced simulations, historical analysis, and international cooperation are critical to ensuring Earth's safety from potential cosmic hazards. This ongoing vigilance underscores humanity's capacity to adapt, innovate, and protect itself from celestial threats that have shaped our planet's history for billions of years. Scientists have explored various asteroid deflection methods in great detail to prepare for potential threats. These strategies range from mechanical interventions to advanced theoretical techniques. Let's delve into each method to understand how they work, their feasibility, and their potential impact if deployed. 1. Kinetic impactor. The kinetic impactor method involves sending a spacecraft to collide directly with the asteroid at high speed. The goal is to transfer momentum, altering the asteroid's trajectory enough to miss Earth. This approach does not require explosives, relying instead on sheer kinetic energy. NASA's Double Asteroid Redirection Test, DART mission, demonstrated this technique by impacting the asteroid Dimorphos in 2022, proving that altering an asteroid's path is possible. While the kinetic impactor is straightforward in theory, successful implementation requires precise calculations regarding the asteroid's mass, velocity, and structure. Porous or loosely held together asteroids could absorb the impact without significantly changing their trajectory. Thus, understanding an asteroid's composition through preliminary reconnaissance missions is critical. The kinetic impactor technique also involves significant logistical challenges. The spacecraft must travel vast distances across the solar system, requiring precise navigation to intercept the target. Engineers need to account for the asteroid's rotation, shape, and surface properties to maximize impact effectiveness. Furthermore, timing is crucial. The mission must be launched well in advance to allow sufficient time for the trajectory to be altered. Historically, kinetic impactor concepts have been tested primarily through computer simulations and limited real-world experiments. The DART mission, however, provided valuable empirical data, reinforcing confidence in this method. Future missions may involve larger spacecraft or multiple impactors to address more massive or fast-moving asteroids. The kinetic impactor approach has also sparked discussions about potential unintended consequences. For instance, a high-velocity impact might fragment the asteroid into smaller pieces, some of which could still pose a danger to Earth. As such, researchers emphasize the importance of accurate composition analysis to determine whether the asteroid's structure can withstand the collision without shattering. 2. Gravity tractor. The gravity tractor method uses the gravitational attraction between a spacecraft and an asteroid to gradually alter its trajectory. A spacecraft would hover near the asteroid and exert a continuous gravitational pull. This force, although minuscule, can accumulate over time to shift the asteroid's path. This technique offers the advantage of not requiring direct contact with the asteroid, reducing the risk of surface fragmentation. However, it requires a spacecraft to operate for extended periods, demanding significant fuel and precise station-keeping capabilities. The gravity tractor concept is based on Newton's law of universal gravitation. By maintaining a consistent distance from the asteroid, the spacecraft's gravitational influence can gently nudge the object onto a safer trajectory. The effectiveness of this method depends on the asteroid's mass, density, and relative velocity. One potential drawback is the time required to achieve noticeable trajectory changes. For larger asteroids, this could take years or even decades. As a result, early detection and intervention become critical to the success of gravity tractor missions. Another critical aspect of gravity tractor operations is the spacecraft's design and fuel requirements. Prolonged hovering demands sophisticated propulsion systems and precise navigational controls. Current research explores the use of ion thrusters, which provide efficient, continuous thrust for extended periods. 3. Laser ablation involves focusing high-energy lasers on an asteroid's surface to vaporize material, creating jets of gas and debris that act like a miniature rocket engine, altering the object's trajectory. This method requires powerful, space-based lasers and precise targeting systems. Research into laser ablation has revealed promising results in laboratory settings. But scaling the technology to handle large, fast-moving asteroids presents significant engineering challenges. Solar-powered spacecraft could provide the necessary energy, although operational feasibility remains under study. Laser ablation technology leverages the principle of conservation of momentum. As the vaporized material is ejected, the asteroid experiences an equal and opposite force, changing its velocity slightly. Repeated laser pulses can incrementally adjust the asteroid's orbit. Challenges include the development of high-energy lasers, capable of operating in the harsh environment of space. Dust and debris from the vaporized surface might also interfere with targeting systems, necessitating adaptive algorithms for real-time adjustments. Furthermore, the effectiveness of laser ablation depends on the asteroid's composition and surface properties. Rocky asteroids with solid surfaces might respond well to laser-induced propulsion, whereas porous or metallic asteroids could require adjusted power settings and targeting protocols. 4. The nuclear option is considered a last resort due to the potential hazards involved. A nuclear explosion near or on the asteroid could either break it into smaller pieces or deflect it with the generated shock wave. However, fragmentation risks creating multiple hazardous fragments, increasing the potential damage. International agreements on space-based nuclear detonations add legal and ethical considerations to this method. Nevertheless, simulations suggest that a carefully calibrated nuclear blast, detonated at a safe distance from the surface, could alter the trajectory without significant fragmentation. The concept of nuclear asteroid deflection has been explored extensively in theoretical studies. One proposed method involves using a standoff detonation, where the bomb is detonated at a calculated distance from the asteroid's surface. The resulting energy transfer causes a portion of the asteroid's surface to vaporize, generating thrust in the opposite direction. However, this approach carries inherent risks. If the detonation results in the asteroid fragmenting into multiple pieces, the planet might face a swarm of smaller, potentially radioactive projectiles. Accurate modeling and testing are crucial to minimize such outcomes. Historical examples highlight the potential scale of nuclear interventions. The 1994 impact of Comet Shoemaker-Levy 9 with Jupiter provided direct observational data on the energy released by cosmic collisions. Simulations derived from this event have informed planetary defense strategies and nuclear impact models. 5. Novel concepts and theoretical approaches. Beyond these established methods, scientists are exploring innovative ideas like using reflective materials to increase solar radiation pressure on an asteroid. Coating an asteroid's surface with reflective paint could enhance the Yarkovsky effect, gradually shifting its orbit over decades. The Yarkovsky effect occurs when an asteroid's surface absorbs sunlight and re-emits heat unevenly, creating a small, continuous force. By altering the asteroid's thermal properties, researchers can leverage this effect to achieve gradual orbital changes. Additionally, some researchers propose the deployment of large solar sails near an asteroid. These sails would harness solar radiation pressure to exert force on the object, altering its trajectory over time. Such methods, while promising, remain largely theoretical and require further development. Historical precedents and ongoing research. Throughout history, asteroid deflection concepts have evolved alongside advances in space exploration. The 2013 Chelyabinsk meteor event, which caused extensive damage and injuries despite its relatively small size, spurred renewed interest in planetary defense. Similarly, the successful redirection of Dimorphos by the DART mission validated kinetic impactor techniques. The Tunguska event of 1908 remains one of the most significant atmospheric explosions in modern history. The energy released during the impact flattened over 2,000 square kilometers of Siberian forest, providing a real-world case study for understanding atmospheric shockwaves and ground-level destruction. Ongoing research involves testing these methods through computer simulations, laboratory experiments, and space missions. Agencies like NASA, ESA, and JAXA continue to invest in planetary defense programs, recognizing the global stakes involved. The role of space agencies and international collaboration, planetary defense, requires global coordination and resource sharing. The International Asteroid Warning Network, IAWN, and the Space Mission Planning Advisory Group, SMPIG, facilitate communication between space agencies worldwide. These organizations oversee observation campaigns, impact simulations, and contingency planning. Joint missions, such as ESA's Hera mission to study the aftermath of the DART impact, underscore the collaborative nature of planetary defense. By combining observational data and analytical resources, scientists can improve prediction accuracy and evaluate deflection techniques' effectiveness. Public engagement also plays a critical role. Events like International Asteroid Day and educational outreach programs help raise awareness about the potential threat of asteroid impacts. By fostering a scientifically literate population, authorities can better communicate risks and secure support for planetary defense initiatives. In conclusion, defending Earth from asteroid impacts requires a multifaceted approach. From kinetic impactors and gravity tractors to laser ablation and nuclear detonations, each method offers unique advantages and challenges. Continued research, technological innovation, and global cooperation are essential to safeguarding our planet from these cosmic threats. The potential impact of an asteroid like Apophis depends significantly on where it strikes, whether it hits water or land. Both scenarios carry severe consequences, albeit in different forms. Impact on oceans. If Apophis were to hit an ocean, such as the Pacific, it would displace vast amounts of water, triggering enormous tsunamis. These waves could reach heights of 30 meters or more and travel across entire ocean basins at jetliner speeds. Coastal cities like Tokyo, Los Angeles, and Sydney would experience catastrophic flooding. Infrastructure destruction, loss of life, and long-term economic disruption would be inevitable. The energy released during the impact would heat the surrounding water, causing steam explosions and altering ocean currents. Marine ecosystems would suffer dramatically, affecting fisheries and ocean-based industries globally. Saltwater intrusion into freshwater reservoirs would impact agriculture and drinking water supplies in affected regions. In addition to the immediate effects, the asteroid's impact could generate atmospheric shock waves, leading to unusual weather patterns and altering oceanic circulation systems. Scientists predict that the environmental repercussions could persist for years, influencing global climate stability. Impact on land. Should the asteroid impact land, the results would be equally catastrophic. The immediate explosion would create a crater up to 7 kilometers wide and over 1 kilometer deep. The blast wave would flatten structures for tens of kilometers, while thermal radiation could ignite fires across vast areas. The heat generated could incinerate forests, cities, and agricultural fields, causing widespread devastation. Moreover, Seismic waves generated by the impact would ripple through the Earth's crust, potentially triggering earthquakes and volcanic eruptions in tectonically active regions. Historical evidence, such as the Tunguska event in 1908, demonstrates how asteroid impacts can flatten vast forested areas and disrupt ecosystems for decades. Dust and debris ejected into the atmosphere would block sunlight, potentially causing an impact winter. This reduction in solar energy could disrupt photosynthesis, jeopardizing global food supplies. The effects could last for months or even years, depending on the amount of particulate matter lofted into the stratosphere. Agricultural productivity would decline, leading to food shortages and economic instability across multiple regions. Regardless of the impact location, the shock wave from the collision would travel through the Earth's crust, causing earthquakes and volcanic activity. Regions far from the impact site might experience tremors and eruptions due to the redistribution of geological stresses. In both scenarios, the global climate would likely experience short-term cooling due to atmospheric debris. This shift could disrupt growing seasons and lead to widespread food shortages. The decrease in temperature could trigger harsher winters, delayed springs, and shortened growing periods in critical agricultural zones. These changes might mimic the climate effects observed after massive volcanic eruptions. The long-term environmental impact of such an event would depend largely on the size of the asteroid and the characteristics of the impact site. If it were to strike a biologically rich region, the loss of biodiversity could be catastrophic, affecting ecosystems for decades or even centuries. Scientists warn that some species might face extinction due to sudden habitat loss and the disruption of ecological networks. Historical records, such as the Chicxulub impact that contributed to the extinction of the dinosaurs 66 million years ago, illustrate the potential severity of asteroid collisions. Although Apophis is significantly smaller than Chicxulub, the localized damage and global atmospheric effects would still pose a considerable threat to modern civilization. Human societies would face unprecedented challenges in the aftermath of such an impact. Coastal populations, which often concentrate in major cities, would bear the brunt of tsunami impacts. Emergency response systems would be overwhelmed, and evacuation efforts would face logistical obstacles due to damaged infrastructure. Economic repercussions would be equally severe. Ports, which serve as crucial hubs for global trade, might be rendered inoperable for extended periods. The interruption of supply chains could lead to shortages of essential goods, including food, medical supplies, and energy resources. Insurance and financial markets would experience significant losses, affecting the global economy. In the long term, reconstruction efforts would require international cooperation and substantial financial investments. Urban planners and policymakers might reconsider coastal developments and implement stricter building codes to mitigate future impact risks. Research into asteroid detection and deflection technologies would likely receive increased funding, driven by public awareness of the catastrophic event. Preparing for the inevitable. While the probability of a major asteroid impact in the near future remains low, historical and scientific evidence confirms that such events are inevitable over geological timescales. The key to mitigating their impact lies in proactive preparation, advanced monitoring, and global collaboration. International organizations, such as the United Nations Office for Outer Space Affairs, UNOOSA, advocate for the development of comprehensive planetary defense strategies. Collaborative projects like the Space Mission Planning Advisory Group, SMPAG, facilitate knowledge sharing and joint planning for potential impact scenarios. In conclusion, the consequences of an asteroid impact, whether on land or at sea, extend far beyond the immediate destruction. Environmental, economic, and societal effects would ripple across the globe, challenging humanity's resilience and adaptive capabilities. Through continued research, technological innovation, and international cooperation, we can better prepare for the cosmic threats that our planet inevitably faces. The future of asteroid detection. The Vera C. Rubin Observatory in Chile and NASA's ENEOS Surveyor mission, launching in 2027, aim to improve our ability to track and predict asteroid paths. More telescopes and better data will help ensure we're not caught off guard. While the threat of a major asteroid impact remains low, history reminds us it's not impossible. The Chelyabinsk event of 2013 and the Tunguska explosion of 1908 are proof that cosmic impacts still occur. By combining our knowledge of orbital mechanics with innovative defense technologies, humanity can stay one step ahead of the next potential impactor. Asteroid detection technology has evolved significantly over the past few decades. Traditional telescopes were limited by their narrow fields of view and manual observation techniques. However, modern observatories now use automated systems equipped with high-resolution digital cameras that can scan vast portions of the sky in a single night. The Vera C. Rubin Observatory, for instance, will conduct a 10-year survey of the entire southern sky, capturing billions of celestial objects and identifying potential threats with unprecedented accuracy. These systems utilize sophisticated algorithms to detect moving objects against the backdrop of stationary stars. Machine learning techniques help filter out false positives, ensuring that astronomers can focus on legitimate asteroid candidates. By continuously monitoring these objects, scientists can predict potential impact risks with greater confidence. Asteroids pose a global threat, necessitating international cooperation. Sharing observational data across borders enhances the accuracy of predictions. For example, astronomers often reanalyze archival images from various observatories worldwide to refine an asteroid's orbit. This collaborative approach ensures that even transient objects, which might only be visible for a short period, are not overlooked. Challenges in asteroid detection. Despite technological advancements, asteroid detection still faces significant challenges. Many asteroids are small, dark, and difficult to observe until they pass relatively close to Earth. Their irregular shapes and unpredictable rotations can complicate trajectory calculations. Additionally, some objects approach Earth from the direction of the Sun, making them nearly impossible to detect with ground-based telescopes until it's too late. To address these challenges, NASA's NEO Surveyor mission will deploy an infrared space telescope capable of detecting heat signatures emitted by asteroids. This will provide critical information about their sizes, compositions, and trajectories, even for objects that are invisible to optical telescopes. The role of public awareness and education. Public awareness plays a crucial role in planetary defense. Misconceptions and sensationalized media reports about asteroid threats can cause unnecessary panic. Educational initiatives aim to inform the public about the realities of asteroid impact risks and the measures in place to mitigate them. For instance, events like International Asteroid Day, observed annually on June 30th, commemorate the Tunguska event and promote global awareness about asteroid threats. Museums, planetariums, and educational institutions collaborate to engage the public through interactive exhibits, lectures, and workshops. Future prospects in planetary defense. Looking ahead, planetary defense efforts will likely incorporate more advanced technologies, such as space-based radar systems and artificial intelligence algorithms for real-time monitoring. Proposals for asteroid tugboats, which could use ion thrusters to gradually shift an asteroid's trajectory, are also under consideration. The development of these technologies underscores humanity's proactive approach to planetary defense. While asteroid impacts are rare, their potential consequences warrant vigilance and preparedness. The evolution of detection technologies. As telescopic capabilities have improved, so too have the analytical techniques used to interpret observational data. Early asteroid detection relied heavily on manual calculations and limited photographic surveys. Today, sophisticated software applications employ mathematical models to predict an asteroid's future path with remarkable accuracy. Citizen science initiatives have also contributed significantly to asteroid detection efforts. Amateur astronomers worldwide regularly submit observations to databases maintained by organizations like the Minor Planet Center. Their contributions augment data collected by professional observatories, enhancing the overall accuracy of asteroid tracking. While current detection systems have identified thousands of potentially hazardous asteroids, the possibility of an undiscovered object posing a threat remains. Consequently, planetary defense agencies conduct regular impact drills to test response protocols and identify areas for improvement. These drills simulate various impact scenarios, considering factors such as asteroid size, velocity, and impact location. Insights gained from these exercises inform policy decisions and emergency response strategies. Collaborative research and policy development. The international scientific community recognizes the importance of collaborative research in mitigating asteroid threats. The future of asteroid detection hinges on continued innovation, collaboration, and public engagement. Advanced technologies such as space-based infrared telescopes and machine learning algorithms have significantly improved our ability to identify and track near-Earth objects. By fostering a spirit of international cooperation and investing in educational outreach, humanity can remain vigilant against potential cosmic threats. As we look to the future, the collective efforts of scientists, policymakers, and the public will ensure that Earth remains safeguarded from the unpredictable nature of our celestial neighborhood. Thank you for watching.